So it's going to take about the full 35 minutes. I'm happy for questions at the end. I'll be around for the ice cream break. I'll get you out in time for the ice cream break, also very important. I want to talk to you about resilience and resilience engineering. In my opinion, it's about 4 things. Infrastructure is one of them, configuration management, which everybody's talking about here today, monitoring and how monitoring sucks, and confidence in deploys. I'll focus on the infrastructure bit because I only have 35 minutes to rant. And I'd like you all to know this is a strictly 2 kitten talk. So kitten at the beginning, kitten at the end. It's all the kittens. So a little bit about my background. I used to work for a company called RIPE NCC. They basically manage all the IP space in Europe, Middle East, and Asia. If you are from the US, they're known as Aaron over here. If you want IP address, go to them. Southeast Asia is APNIC. After that, I went to Canonical, and I ran the server engineering team there for 10.04 and 10.10. I'm very proud of it. I have a question for the kind gentleman in the back with the red hat. Is the red hat symbolizing your association with the Red Hat operating system?
Yes.
Excellent. I look forward to having a few questions with you later today. So anyway, 10.04 was the first series release for EC2. 10.10 was a pretty good big improvement. 10.04 is the long-term support release. That's why we cared so much. I still think it's the best one in EC2 to use. Ubuntu, that is. It's definitely the most popular one. I think they have over 50 or 60% market share of stuff that's being launched on EC2. So after that, I went to a company called Krux. I was one of the first hires there, and I run operations. So all the toys that I built at Canonical and before, I now get to actually run. What we do is think of it in terms of Google Analytics for audience data rather than for traffic, or that thing that Netflix does to figure out what you want to watch, or that thing that Amazon does to figure out what you should buy. We just kind of do that for user data in general, so recommendations, analytics, all that kind of stuff. We like to think that we're the good guys of data privacy. We make sure that consumer data stays between you and the website you're on. So when you're on New York Times and we do the analytics for them, it's the 3 of us that have the data and doesn't leak everywhere, which is like a big problem with advertisers and so on. So quick list of our customers, and let's just illustrate. These are some big properties, and for every request that they get, we get one. So we deal with quite a bit of traffic. It turns out, especially the data privacy angle is acute in Europe right now, where the regulations is much more strict than in the US, so we do all their data privacy handling for them as well. So in essence, lots and lots of traffic. Aside from the traffic, we are on the critical path of delivering many of these pages. So the New York Times homepage, if we mess up, you will notice. And that's generally considered a bad thing, both by the users and our customers. So we try to avoid outages at all costs. So to put some color to the numbers, and I'll say right away, there's a bit of an apple and oranges comparison, to just give you an idea. This is the amount of requests per second. The top one's Twitter. Their average request rate is about, or new tweet rate is about 5,000, a little bit over. Wikipedia gets more articles read than that. Go Wikipedia. We do about 10,000 new data points a second. Twitter does more with their new tweets than we do with new data, so again, this is a little bit for color. Our reach is right now about 530 million users a month. I think Wikipedia is up in that area too. 500, there you go. Twitter, not as far. But that means that we get lots of data for lots of users, which we need to process in real time, we need to store it, we need to do the analytics, and we need to give answers on all the time. So we have a data store that's about 600 million keys, which gets accessed all the time, and it's about 200 gigs of raw data that we process, a large chunk of that in real time and some of it in batch. So we had to choose how to deploy, and we chose the cloud, which is hopefully one of the last times I'll have to say that word during this presentation. I think we can all agree that we can't agree what cloud means. But the good thing about cloud is that it's really good if you're a startup that's growing fast. Like you don't have to really think about how much you're going to need in the next month or two. You don't have all these problems of getting the hardware into the rack and set up and so on and so forth. And as our early customers like New York Times and Forbes were coming on board, they have serious request volumes. This is like hundreds of millions of impressions. And it was pretty easy for us to say, okay, well, we'll just put 10 new servers in and fast. So it's really low CapEx. The downside is really high OpEx. Anybody who's got a big enough cloud deployment, Netflix, will know that it's really expensive to run this stuff. But the good point is it's a controllable price point. It's no upfront investment. So we felt pretty confident as a startup we could build on this. And EC2 specifically gives you tons of components to build off of. Now, it sounds all awesome. Unfortunately, it's not all awesome. Your failure modes are completely different. What you're used to in a data center doesn't apply in the cloud anymore. Like in a data center, you have a network that you can control. You can probably put a 10 gig Ethernet cable between your master and your slave, and you can be pretty sure that cable's not going to break. In EC2, all bets are off. You have a node over here, you have a node over there. Who knows what networking equipment is in between? It might even be in a different building. Your friends from Netflix might be on the same network as you, transcoding like crazy, and all of a sudden you get packet loss. That stuff happens. There is no way that you can add an extra power supply to that machine that you really care about. That you're like, you can't hook up a diesel generator. You can't do crazy RAID drives. Battery back RAM, that's not an option anymore. So things can fail, and there's nothing you can do about it. You just have to deal with it. So for the talk specifically, I'll focus on AWS. It's the biggest one in the infrastructure space right now. It's the most fully featured. At Ubuntu, we target it. At Krux, we use it, so I feel most equipped to talk to it, but it applies to most vendors that you use. So a quick little history for those of you that were around in April 21st, 2011. If you were on the cloud back then, it was the first big EC2 outage. Maybe they've had them before, but that was the one that we all noticed. Lots of companies were affected, like Netflix was out, everyone was out. And the stability and dependence of something like EC2 was immediately questioned. It's like, can I build my company on something like this? I'm totally dependent. If it falls over, it's done. What do I do? And it turned out that the failure that happened was such a small thing, such an easy thing that could have happened. It was a network change. Somebody changed a network. It was a cascading failure, took down their EBS solution, which is their SAN solution, RDS, their hosted database, and most other network services. The network was hosed on their backplane. And the good news was the elastic load balancer stayed up, which saved our ass at the point. But all big companies were down. Everybody did this big postmortem. Netflix put up theirs and saying, we understand exactly the failure. We're going to compensate for it. We know exactly what to do. We are educated. So I'm going to skip a bunch of outages for brevity. And then go to June 14th, which was the second to last big one. And it had the exact same symptoms as the 2011 outage, but this time it had a different root cause. Their SAN backplane just blew up, which means all of your EBS, all of your persistent data volumes were unavailable. When they came back, they probably weren't clean. We had a bunch of them didn't mount up anymore. It was just FSUC came by and went like, no, go away. Which meant that EBS, RDS were unavailable. Basically, your two main data stores, if you have a traditional LAMP stack, gone. Again, Netflix was affected, slightly smaller scale, same postmortem came by again. And then, just when you thought it couldn't get any worse, 2 weeks later, June 29th, it was another big outage. This time, a thunderstorm messes up everything on the East Coast. Now, US East is their most economical, their largest data center. It's their best connected one. It's great if you're US and Europe based because you have pretty decent latency either way, so a lot of people are there. And yeah, so the thunderstorm came by and it broke everything. The ELBs, their load balancers, had some latency spikes. Their API was down, so even if you went in and it's like, oh, I need to just change something so it'll go from A to B or spin up a new machine, no dice. So US East was mostly unusable. Apparently 7% of the capacity of the AZ was just dead. It was just blown up, threw it away, and most other people just suffered a latency spike. Now, this is something that nobody could do anything about. Like even the guys at EC2 was like, how did you not protect yourselves against a crazy thunderstorm that actually claimed lives? Like, and Netflix is down. You have to have a little bit of perspective there. But if you can't redirect your traffic away from that point, when like the provider you use doesn't even have an API that is usable at the moment of an outage, your host. If you can't redirect, you will be down. And all these people, they were down. This is what happened to them. Reddit, Quora, Netflix, like, you use most of these services. It also made me realize that you shouldn't have red in your logo. I think that's like, it's the biggest lesson I take. As long as you don't have red in your logo, even a small Instagram, you'll be fine. But on the flip side, we withered all of those 3 outages. We didn't lose a significant amount of data. We had some degraded API calls, but everything was operational within tolerances, and our main base of operations is out of US East 1. And we did tons of stuff to make sure that we would withstand this type of stuff. Now, in our case, we have enterprise customers. We have SLAs that are pretty stringent, but their companies themselves are consumer-based traffic. So they have very light traffic numbers, and they can put up a fail whale, but we can't. So we had to architect for that. So the big thing is the rules have changed. You thought about data centers, you thought about how to compensate for that, and things are differently. you have different strengths and weaknesses, and you can use the new strengths, and you have to compensate for the new weaknesses. So you basically have to change your entire architecture as a result, and the new truths that are there. One of the big ones is your network will partition. It happens all the damn time. I'm sure most of you run something in EC2 or you wouldn't be here, or at least in an environment that you can't quite control. We see it for a handful of seconds. We see it as long as 24 or 48 hours. A node just goes away, and then it comes back. No idea why, it's just gone for a bit. This one is the most infuriating one for us. It's disk I/O. I wouldn't even care what the I/O was, as long as it was some band of tolerance that I could predict, but it's just, it could be anything. And the reason is you're in a multi-tenant situation. You're sharing the I/O channel with everybody else on the box. The smaller your instance type is, the more of them that are there, the higher the fluctuation will be, because only one of them really trying to saturate the channel is going to negatively impact everybody else. If you go out to EBS, their SAN solution, you're now going over this shared network pipe, which again, if somebody's pumping tons of data through that, you're going to be affected as well. So noisy neighbors can totally affect your throughput, and we just now stop trying to figure out what's going on. We just mutter something random about Netflix being bastards, and we move on. Something that would never happen to you in a data center, your IP addresses change all the time. You're encouraged to use CNAMEs inside of Amazon. They have a 60-second DNS TTL. There are DNS implementations out there that won't honor that TTL because it's so ridiculously low. And you have to deal with that. And then there are systems that can only deal with IP addresses. If you look at Cassandra's ring configuration, that's IP addresses. That is not host names. If you look at varnished backend declarations, they will do a host name lookup on startup. So if you say my backend is foo.example.com, so it's no problem. What's the IP address? 1234. Awesome. That is what I'm using from now on. So if that changes, stuff breaks. And then my absolute favorite one, shit will just die. And rule of thumb says if one of your instances dies out of 100, it's your database master. It's always your database master. It might be a hardware failure. It could be a bug in the host. You could have accidentally killed the wrong thing in the UI. You clicked the wrong button. Like, stuff happens. Feel free to come in if you want. It might actually be one of my colleagues at Canonical. This was one of the things that we found absolutely awesome while we were working there. Amazon doesn't offer a development environment for kernel development, but they allow us to upload them. So when we test a new kernel, we build one, we upload it to Amazon, we launch an instance, and sometimes the instance wouldn't come up. We're like, oh, that's weird. And then we got somebody from Amazon saying, hey, your new kernel is not quite stable, just took down the Zen host. So if you were in the same instance as us, well, sorry, it could have been us if your shit died. And then all this stuff aside, I mean, you have humans in the mix, and like they do dumb shit. It could be not hardware failure, not poor design. It's humans. Like AWS employs humans. They work really hard. They do the cool and smart stuff, but then sometimes it breaks. It could be your humans. They do dumb shit too. And your real job is to mitigate the impact of all of these failures. This is the best you can do, and it is what you should be doing. So this is our new mantra. We just embrace failure. Things will happen. And even if it's not the humans, if it's not the hardware, nature will throw you a thunderstorm. Deal with it. So what can you do? Well, first of all, it's don't bring a knife to a gunfight. Change your game plan. What worked in the data center probably won't work in the cloud. If you build your traditional LAMP stack with your MySQL master and your read replicas on it, and you store your stuff to disk, and it'll blow up. It'll hurt. So you're going to have to deal with the new constraints presented. But at the same time, there's some benefits in there, the ease of spinning up things, the ease of having the instances when you want them, that can make your life a lot easier. And I'll try to get in both. So in my opinion, the biggest thing to deal with is picking the right data store for your problem. Is anybody here not familiar with the CAP theorem? CAP, C-A-P. No. Okay, no worries. We'll get into that. So I conveniently prepared a slide for it. So the CAP theorem says you can choose between consistency, availability, or tolerance to partitioning. Now, because we already talked about network partitioning being a fact of life, it's like cheap, fast, good, pick any two, except you get to pick one, because network partitioning is just a fact of life in EC2. So your choice is, do I want my database to be consistent, or do I want my database to be available? That's your two choices. So you can sacrifice availability, or you can sacrifice consistency, if you want to look at the glass half empty version. I wrote a bunch of names down there that you probably remember, like CouchDB, anything Dynamo-based, like DynamoDB, Riak, Cassandra, Bigtable-based, it's H-based, Bigtable itself, obviously. Any traditional database, like MySQL and so on, they're all on the consistency side. Like if a write works on the master, it has to make sure that it gets propagated, otherwise the write fails and bad things happen. I didn't put SimpleDB on there because it doesn't scale beyond 25 writes a second, assuming we all have bigger constraints than that. So if you want to go the traditional database route, and there's definitely a bunch of frameworks that would like you to store your data in a traditional database. Django is definitely one of them. I think Ruby's Active Record would really prefer you to store it into something SQL-y and maybe not H-based. Amazon offers RDS. Your two choices are Oracle or MySQL on that, and then they do the entire hosted environment. You can get a hot standby. You can get as many read replicas as you like. The downside is it's a 7-minute failover. So when your RDS master dies and your hot standby gets the data and everything reconfigures and you start reading from there, that's a 7-minute window. Hey man, come on in. That is a very long time. That is an unacceptably long time. But it is better than anything you can do. That is the flip side. You can't replicate out of RDS yet either. They keep telling us any time now, but I haven't seen it yet. So like pick your battles. And in general, I'd say if you have to run traditional MySQL, SQL-based stuff, run RDS. You're probably better off. But it comes with some pretty serious constraints. So the other type of storage you can use is HBase. HBase is built on top of HDFS, the Hadoop file system. I'm sure most of us are familiar with that. There's a version called Cumulo, which is basically similar to HBase, but they focus very heavily on security stuff, obviously, because it's built by the NSA. And then there is a Hypertable, which is another implementation with a similar design. They all have the same problems with network partitioning. Writes will fail if the consistency level can't be reached. So if you tell HBase, I need 3 copies of this data, and it can't give you 3 copies, as the write failed, you deal with giving me the write at some other point or whatever you want to do. HBase still has a single point of failure on the name node. It has a recoverable but single point of failure on the region server as well. So it can be recovered pretty quickly, but you can only have one, and when it fails, too bad. There's patches out there that Facebook uses. They haven't been integrated yet in the mainstream. There's a company called Cloudera, which releases basically the commercial version of Hadoop. It now comes with HBase. It's probably the best version you can get out there if you're not comfortable running just the latest release and being on your own.
We're testing CDH4 right now.
How is it?
The ops guys that are working on it seem to like it.
Yeah, it would be definitely my recommendation. Like if this is the pattern you can live with and what you want, CDH is probably where you want to be at. But it can and will break in certain places.
They are pretty responsive for
yeah.
This is broken.
Yes, yes, yes. But when Amazon has network partitioning all over the place and you simply can't write from certain nodes to certain other nodes, there's like very little you can do. This is by the nature of the thing. HBase promises you when you write, and I told you you wrote, then you know about consistency levels, you know about all these things. This is a promise I make to you. And obviously Google App Engine uses this too. Your other alternative is any Dynamo-based storage system. So they go with eventual consistency rather than consistent on when the write happens, which means that you can accept the write on any node, and then the system itself will figure out how to propagate that write. And the promise is eventually that write will be propagated. DynamoDB is one of the implementation that is hosted by AWS itself. It is fast. It is has good performance, has good reliability. It basically has all the great features except that the charges per IOP, which means every read and every write costs you money. I know. It's on an SSD, so it's worth it, right? And SSDs cost millions of dollars, so it's reasonable. So we did the napkin math. In fact, actually, the Amazon guys came by before Dynamo came out and said, hey, looking at your patterns, you should probably be using Dynamo. Can we pitch it to you? Would you want to try it? And I said, sure. Let's write down some numbers on a napkin and see what the total amount of dollars comes to before we have this conversation. So I gave them some numbers, and they did the napkin math, and then they looked at the napkin, and they grabbed the napkin like this and threw it in the trash and went like, let's talk about some other solutions that we might have for you. 5,000 reads, 1,000 writes per second on a 2 terabytes of data is $6,000 a month.
Or not.
Or not?
Well,
as in, you don't want to do that.
Do that.
Exactly. At low rates of writing and reading, DynamoDB is awesome because you're not going to rack up that cost. It'll respond quickly. You can be pretty sure it all works and stuff, but just at the volume that we write at, Now, we got like 10,000 new things coming in every second that we want to write. At this point, we're paying them tens of thousands of dollars to write it in the system. Anyway, so Riak and Cassandra are good options to consider. We run Cassandra. There's a company called Basho that offers Riak Enterprise for a great price for startups. They'll give it to you for next to nothing and hope that because you love it so much and your company grows, you'll go to the big boy version. DataStax is the company that does the enterprise version of Cassandra, and we think it's totally worth getting as well. It's a straightforward pricing model, nothing crazy. The other great thing is that both Riak and Cassandra have successful referenceable implementations on EC2, and I think they're the best suited scalable store in AWS right now if you're not going to go with one of the Amazon solutions. We were very hard pressed to find a successful HBase implementation. We found one big HBase implementation in EC2 who told us we moved away from HBase in EC2 because it's just that hard to run. Obviously, you can make it somebody else's problem as well. That's usually a pretty good strategy. You could rely on a third party. Most of these technologies are quite new, however, so that means that their commercial hosting companies are even newer than that. Some aren't even out of beta yet, so if you're going to go with somebody else hosting this stuff for you, you will be a guinea pig. Understand that when you're building your system. It's not a silver bullet. So I linked a few for convenience. The slides will be up after the talk on SlideShare. The link will be at the end. You can click on them. CouchDB has one, Riak, Cassandra, HBase. I'm not sure if you can quite tell this, but you see the tiniest little white dash between these letters? Sure. Yeah, that's because every letter is a separate link. So all of these companies have one commercial company. Mongo has like seven. 7 commercial companies that run Mongo for you. All right, so you have your data store. You also have to deal with your local disks. AWS gives you 2 options for a local disk. 1, instance store. It's usually faster, but I/O can fluctuate like crazy. You're on the local host. You're sharing it with everybody else on that local host. Again, if Netflix is transcoding videos, expect dips, expect higher I/O wait times, everything. The good news is a reboot will retain the data. The bad news is a start and stop won't. So consider how much you care about the data. All of our Cassandra nodes use a software RAID over all the ephemeral devices that we have on localhost. It's the fastest performing thing. And our redundancy is by the fact that we have multiple copies of it. So if nodes go away, that's fine. The other option is EBS, the SAN. It has a guaranteed baseline, so the I/O is much more consistent, but it's definitely slower. Now, some instances, M1 largest, M1X largest, and 4X largest have an option of a dedicated EBS IOPS for to 500 or 1,000 Mbps. That's pretty good, but there's definitely a price tag again. And if you really have money to burn, because it's a crazy time in Silicon Valley and everybody can, they have one massive high I/O SSD-based instance, which will cost you $3.10 per hour, or the equivalent of 10 M1 larges, which are basically better than your laptop. Anyway, in all cases, you can totally RAID the drives for improvement in performance, which is what we do. Pick RAID 10 if you can't reproduce your data effectively. We have a lot of our the data that we serve in a raw form in S3, so we can use MapReduce to really quickly repopulate the data. So even in a catastrophic failure, it'll be about an hour, hour and a half before we have it fully repopulated again. And my best advice is, if you have anything that's front-facing services that need to hit disk, use Instance Store. You'll be so much better off. Because if nothing else, EBS is still going over the network, and network partition does happen, so there are also times that you can read your disk. All right, so next one. The best thing that Amazon has ever done, ever, anywhere, ever, is S3. It is a ridiculously highly available thing. It's almost impossible to get down. We've had a failure maybe happen in a read or a write, the retry resolved, and it worked. That's about the failure mode of S3. We've never had anything bad happen. It will be available when nothing else is. It's HTTP based, and most languages have a binding for it. Anything that we need to be available, and we use our Puppet ENC as in S3, because it won't be down. There's no MySQL that can blow up, no networking, S3 will be there. If you care about your logs, just push them via log rotate, cron to S3. We do that every 15 minutes. That's where a bunch of our raw stuff comes from. Compress them. It'll save 80 to 90% of your S3 bill. That's a big thing there. I tried out a hack to use Fuse on top of S3, so I could have a local file system that was backed by S3 and see how it performed. The I/O is crap. So the latency is so high that it doesn't really support a lot of reads and writes, but it's the file system that won't go away. So much about files. The other side that you have to your disposal is traffic shaping. Although you don't have control of the network inside of EC2, you can definitely control the network that flows into the network of EC2. This lets you define any type of mitigation strategies, like serving from a local cache, serve stale, degrade, or reroute. So how do we do that? First of all, stay local if you can. If you go off box, you're just increasing your risk. So if you have an HTTP server and you have your backend on another server, you now have 2 single points of failure that the user has to go through, and the odds that one of them fails is much higher in combination. Sorry, that the request fails because of that is much higher. You actually have to think about things like degrade gracefully when you can't reach your database, or you can't reach your disk. This can and will happen. Work async if you have to go off box. Scatter gather is a really good way to go about. Remember the log files that you want to write to disk? They can be written after the request. Don't wait on the write to complete before you finish your request. It's little things like that. And if you have to go out of the box, try to stay into the same EC2 zone. If you go into a different zone, like US East 1A to 1B, you're crossing some boundary. Often you will be going to a different building. There's a physical network that needs to go between them. There are people that do road construction that can and will at some point break that cable. So obviously, cache what you can. I think that's a pretty obvious piece of advice. You can cache HTTP responses, database queries, user content. Browsers have caches, something a lot of people will forget, and we're going to get to that in a little bit. We use Varnish to cache stuff. We have a reasonable TTL on the cache itself. We have a grace of 2 to 3 times that TTL, meaning that if you come back for the thing that we think should take about an hour to refresh, but it fails, we will serve the stale copy rather than giving you a failure. In other words, we tell the client after an hour come back for a new copy. You come to us. We can't get you a new copy, but we still have the previous copy that we served you in cache. So for the user, everything looks dandy. It's just slightly out-of-date data, which in most cases is fine. And it's in 99 out of 100 cases better than no data whatsoever. Financial applications aside, probably. So Redis and Memcache can be used for blob stores for SQL results or JavaScript snippets. That's probably pretty common. And it's actually the picture that I'm most proud of in this slide. It's a bag of $220,000 in cash by a guy called Matt Inman, or the Oatmeal. You guys? Yeah. Okay, so you all know the story. The link is down there at the left, and it's an awesome story. And one day I hope to walk around with a duffel bag with that much cash in it. All right, Elastic Load Balancer. This is what saved us each and every time. When I told you that we withered 3 big storms in EC2, this is why. The way they're done is very, very clever, and they're very economical. We push 30 terabytes of data through these ELBs, and we're being charged $400 for that. You're being silly not to use them. They autoscale and rebalance as needs to, and it beats running any HA proxy instance that you can come up with. It's simply better. And the reason for that is that they're a combination of both DNS-based load balancing over the active region that you have, as well as appliance-based EC2 instances. So they can balance over instances, but they can also balance between zones using networks. So if one zone is being degraded, the DNS will tell them never to go to that zone, which is something that you can't do with your HA proxy because you're already in that zone when you've accepted the traffic. So when nodes or zones fail, the ELBs will adjust traffic accordingly, but they only work per region. Only US East, only US West, and so on. So we use global load balancing on top of that. Now, if you care anything about your website, and sorry again to rag on Netflix, I think they run mostly out of US East 1, you should be in more than one region. For one, you give your users much better latency. If you're on the West Coast and you can go to a West Coast data center, that's better than going to an East Coast data center, it's better than going to Europe. But it also lets you fail over. So that diagram is how we fail over. So if you take the one in Ashburn, Virginia, if that one fails, we'll reroute all US traffic to the west and everybody who's coming from Europe or to the East Coast to the east. And that means that in our case, we choose 15 minutes. So in 15 minutes, in case of a thunderstorm knocking out all of the East Coast, at which point the internet has bigger problems whether we're up or not, but it'll take us 15 minutes to move all of our traffic somewhere else. And that's just a knob that we draw with how many DNS requests do we want users to do on an ongoing basis so they can get that up-to-date information. Your DNS provider probably has a way to monitor your individual data centers. It probably has a way to do this for you. If your DNS provider does not, you might want to consider using a different DNS provider. If you're a US-focused company, US East 1, US West 2, those are your best regions. US West 2 has actually newer hardware at the same price point, so it performs slightly better, even though Amazon will tell you it's all the same. And what we do in this case is also use weighted DNS rules for new versions of code. So we'll roll out one data center with new code, but we'll migrate all the traffic away from it and then slowly start trickling it in again and see if the new code does better than the old code and see how it does performance-wise. And we do the same thing with upgrading data centers. So if we do things where we actually need downtime, we'll just send the traffic away from that data center and then bring it back when we're ready. What the user pays is like 100, 200 milliseconds worth of latency in the worst, worst, worst case. So speaking about going with a good DNS provider, I can't rave enough about these guys. They're our DNS provider. They do it for Bitly, Quora, Twitter, and so on. They're awesome. They know what they're doing, and they will offer great support in getting you where you need to be. So I'll always give them a big shout out. And without them, at the last AWS outage, we would have been hosed, right? Because we couldn't change anything in the US East configuration. So if we couldn't change DNS, we'd just be hosed. I'm pretty sure I'm preaching to the choir, but use a CDN if you're not yet. If you're getting started, think about CloudFront. It's pretty decent. If you get lots of traffic, maybe think about a company like Fastly, who offer really good performance. Even the smallest bit of caching can help you. A TTL of 5 seconds with a grace of 5 minutes is the difference between your site being down for 2 minutes and the user noticing and not noticing. 5-minute old data is usually fine. All right, and then the last bit, which I think is one of the most underused things in your arsenal, is to utilize the client. You can totally do that. Whether it's a browser, whether it's a mobile app, whether it's a desktop, it should be part of your resilience solution. You can store data there. You can compute changes there, and you can gracefully degrade. If you're not getting back what you expected, you don't have to throw an error. So client-side storage is like the thing. Not all your data needs to live on your servers, or at least it doesn't only need to live on your servers. Your older data can be provided by, your older data can provide a reasonable fallback when your servers aren't reachable. And that's what client-side storage is for. You get 5 megs per app or per domain in most browsers. That's a lot of client-side storage. It's a lot of JavaScript, especially if you feel like compressing it. So I'd like to take the last 2 minutes and just bring this all together in how we make one service pretty much bulletproof. So we have a service that's globally load balanced, which is cached by Varnish, which reads from a data store and returns JSON to a JavaScript client on a popular web page, say the front page of the New York Times. And that kind of looks like this. So the colors that are in there indicate how bad it would be, relatively speaking, if one of these components failed. And we'll go through the failure modes. So the worst thing that could happen to us is if our JavaScript has a bug in it, because then you can't really predict what's going on. But as you notice, the data store going away is about the least of our problems. And it's also one of the most frequent things that will probably happen to you. So here's a sunny day scenario. The user makes a request through the browser. Let's say they hits the East Coast, hits Varnish. Varnish goes to the app, says, give me whatever the hell the user wants. Looks it up in the data store. They get the answer. It goes back to the user, and it goes into browser storage. This is pretty straightforward way of doing things. What we do on top of that is we put a copy inside local storage. So we got the response. It's in browser cache. We take that same copy, we put it in local storage. We're now starting to prepare for failure because everything went well, and there's no guarantee that the next one is going to go well as well. So we set a generous cache control header on that response and saying, like, you can keep that for as long as we think you should be able to keep it. Now, let's say something goes wrong. On the next request, the data store node can't be reached, or it doesn't return in time. The first level of workaround is that the app will retry different nodes. But at some point, you're going to have to give up, right? I don't want the user to sit there for the HTTP timeout of 5 minutes while I retry nodes. Maybe 500 milliseconds, 50 millisecond timeout, give me like 8, 9 tries before I give up. If I don't have anything then, the odds that the 11, 12, or 13 tries going to give me something are next to 0. At that point, the app still returns a 200, but with a JSON blob that says, I couldn't get you any newer data. And that travels back to the client. Now let's say that the app fails. Varnish figures that out and returns a blob to the user, to the JavaScript and says, I couldn't get you any newer data from the app. And now let's say that Varnish fails, at which point the load balancer will simply yank the node. And let's say that in the worst case scenario that the entire East Coast fails, our global DNS will switch over to the West Coast and the whole thing starts over again. Now when we send you this synthesized response, we set a very low cache control header. I'll explain to you in a moment why. So, now the client side and why this works and gives you resilient solutions. At this point, because the browser made a new request, the old cache copy has been expired, right? You told it to keep me for an hour, I make a new request, I have a valid response, throw away the old one. When the client receives a response indicating that no new data could be provided, then it will fall back to the local storage and say, what did you have before? The one that I know that was fine. on that response that we couldn't give you any new data, we set this lower cache control header, which means that you're not going to be refetching every time. Because the odds are, if our backend is down, we have problems we need to fix. And the last thing that we want is a stampede the second that things back up again, which will probably knock the service back down again. So this is how we spread out the amount of refetches that need to happen. So the bottom line is that in a normal case, we can rely solely on cache control and just dial that knob to where we want to be in terms of the amount of requests per second that we want to handle, in terms of staleness of data, and so on. But in the degraded case, when even cache controls expires, when known good previous responses would have been thrown away, we have a backup. The worst case degraded case, when an entire app or data storage plane is gone, is that you're using slightly outdated data on the client that you're probably not going to notice. So that's how we tie the whole thing together. At 34 minutes and 59 seconds. Sleep tight. Any questions? Go for it.
The Cassandra nodes are on AWS instances?
Yes.
And you have 10,000 writes a second?
Do you know the numbers out?
With after these ones, it's a couple thousand.
Yeah. So the Cassandra nodes don't do 10,000 requests a second. We have multiple storage systems. We use Redis as well, which is taking a bulk of the writes. And we have lots of writes that we stream over a TCP socket to be processed in real time.
Okay.
So they're...
I was going to say, that sounds really expensive, but that sounds a lot cheaper.
Actually, it is doable.
Yeah?
It is totally doable. Your bottleneck will be how fast your disks move. So if you just plan for that capacity, you can do it. And extra nodes will actually give you the performance that you need. Any other questions?
What do you use for storage in Cassandra?
What do we use for...
For storage in Cassandra.
How do you mean specifically? Whether we do it on EBS or...
Do you use EDS or?
No. We use local storage. We have an instance size that gives you 4 or 8 drives, 4 drives that we software rate together. And that means that we get 4 times the write performance out of it because it's 4 drives.
DNS. So we migrated away from Dynamo because it was more expensive than what we really need. So we've actually migrated to Route 53 so that we can put elastic load balancers at Apex records.
Mm-hmm.
We cannot do without Route 53. So are you guys just not doing that?
We are indeed not doing that. We found that Route 53's DNS is not as good as Dyne's, the DNS lookup times. So what we do is we're in the critical path of loading. So as you request something from us, the DNS lookup is part of the request time for the entire page. And those numbers were relatively high, and on Dyne they're really good. So for us it was worth it to optimize that part. But that's a very smart solution. So if that fits your use case, yes.
And there is actually supposedly coming soon for the last year and a half slave support for find masters.
Mm-hmm.
In the meantime, CLI 53 is okay, but so you can do synchronization pushes, but the API does not allow replace, so you have to do a delete and reassert. So if you have lots of requests, there might be a limit.
That's it. And so what I didn't tell you about is the amount of reads per second we get in total. So 10,000 is the amount of writes we get. Reads spike up to 30,000 a second in total.
So that'd be problematic.
That would be problematic for us, yes. But not everybody has to deal with this traffic. So if you can deal with the tiny, yes, absolutely. Any other questions? Go ahead.
May not be relevant here, but this one more. Have you heard of a database by the name VoltDB?
VoltDB? Yes.
The reason I'm asking the question is we have a problem with our, all these things that you described.
Mm-hmm.
What if something's bad, something?
Right.
Do you think database is the main issue for most of the applications?
If you write your app stack like you probably did back in the LAMP days, where you would basically go all the way through the database most of the time and maybe do performance optimizations using memcache or something like that, yeah, database becomes your bottleneck. And usually you have one master, so then you can't accept writes, and most things can't deal with that.
Assuming that we handle that differently.
Mm-hmm.
So it seems that Vault database is supposed to give you probably best advantage in terms of memcache, in terms of in-memory, in terms of sharding and all these things. And I just want to know whether you had any time thought about it. It might not be supported directly on the Amazon services, but if you had your own co-location facility, would you be using something like that to address all the issues
I would definitely try it out. I have to say that we were fairly biased towards known working solutions in Amazon. And because we know the characteristics of Cassandra really well, we have a guy on staff who basically knows Cassandra inside out, which was a big reason for us to consider it. And we know that HBase was a viable thing for our solution as well, so we narrowed the scope of what we looked into. So I can't actually speak to VaultDB, but had I done the research, I probably would have looked into it.
Other things.
No worries.
With your really low latency requirements, do you have to, in your eventually consistent pattern, are you doing like really low read forms with really fast timeouts to make sure that you're getting a good, because in the cloud, it seems with Cassandra and whatnot, you can have a couple of nodes really make your not terrible for you if you have a,
Exactly. So, you know, do we do low quorum reads? Yeah. So for us, it's can we give you an answer, and depending on what you're looking for, the latency requirement changes and the accuracy of the answer changes. So let's say that I need to make a recommendation for an article you should read. If I know that you're already a fan of X, but I could have known that you're a fan of Y, just knowing that you're a fan of X is actually good enough. And I can know that you're a fan of Y later. If you're asking me to compute your bill, I'll do a higher quorum read and just make really sure that we bill you for everything that you did. So yes, absolutely, we do quorum reads of 1 for most stuff, but we do writes for 3.
with like a really fast timeout so that
Yeah, exactly. And that's handled in the app. So the app can say, hey, I'm on the critical path of delivering stuff, so I'm going to give you 20 milliseconds to give you an answer. Our 99th, so we no longer track average response times because we don't care. We just track 95th and 99th. We only care about the 99th, and we track the 95th on our graphs as well to just see if the 95th moves with the 99th to give you a visible idea of whether that's bad or not. And in most cases, our 99th is well under 10 milliseconds, so we give it 20 to 30. And we know that if that happens, then you're in some case that we've never even seen, so just shoot it.
to deal with like compaction tricks to make sure it's mostly in memory so that you don't have to worry about compaction.
Exactly. Cassandra has tons of knobs and dials that you can turn, and we've been turning and dialing those knobs like crazy to get those numbers as efficient as we can. When MapReduce runs and we get the most writes at the same time and we touch a lot of keys, we see it spiking up towards those 20 milliseconds. So we go from like 10 at the 99th to like 20. So we can definitely tell that we're making it work very hard, and then we have a compaction strategy that immediately rectifies all the changes that we've done. Anyone else? Would you like ice cream?
Yeah.
Go! Thank you.